we have been looking at gradient descent, right? Like, which is an iterative algorithm for finding minimum for any loss function, right? So towards the end of the second session lecture, we talked about the implicit bias or regularization effect of gradient descent, right? Like, which is to prefer low norm solutions, like, hence, even if you have a 20 parameter but 10 examples, like, so you are not going to go. Someone asked me this question in the break. Was it you? Like, so it's okay. One of you asked this question in the break, like, would it be the case that if I continue training this for infinite epochs, eventually gradient descent will overfit like the closed form solution? The question is, if I keep doing gradient descent, okay, in theory, infinite number of epochs, right? Like very, very large number of epochs, would it arrive at the same overfitting solution as the closed form solution? What do you think? Maybe I should have kept this question for midterm. Okay, I'm not going to give an answer for this question. Okay, so to think about it, I might ask this in the midterm. Okay, so now we're going to talk about regularization for the rest of the lecture. Okay. So we'll start with L2 regularization, which we have already seen in the previous week, right? So with L2 regularization, you would have the typical error plus lambda times EW of W, where the typical training error is given by y minus xw transpose y minus xw. Well, you could put a 1/2 beginning, it doesn't matter. So then you have EW of W, which is just W transpose W, right? I'm going to redo the gradient, like the minimization that we did last week, just as a recap. So with L2 regularization, we want to minimize this modified objective, which is y minus xw transpose y minus xw plus lambda times w transpose w. Right? So I can differentiate this and set it to 0, which is what we did last week, right? Like, which basically gives us minus 2 times x transpose y minus xw plus 2 lambda w is equal to 0. So I can write this as okay. So I'm going to skip all the steps and write it as x transpose x plus lambda I times w is equal to x transpose y, and w was x transpose x plus lambda I inverse x transpose y. I skipped a bunch of steps here, like, so you simplify this, take things in common, like, so you arrive at the solution, right? Now, the solution that you arrived at looks very similar to the original least square solution, except for the fact that you add lambda I to the matrix before inverting. Okay, so what does this mean? Like, this means that I'm adding a small positive value, lambda, to the diagonal of the matrix before inversion. Okay, so someone pointed this out during the break in the morning. So this is actually one way to ensure that the matrix is invertible. Like, if you add a small positive value to the diagonal, it actually makes sure that the matrix is invertible. Okay, that is a side benefit of using L2 regularization. When you use L2 regularization, it's easy to do closed form solution because, like, your matrix becomes invertible. Is that clear? But the main benefit is you are reducing the norm of the solution depending on the strength of lambda. Okay, so this idea of doing L2 regularization with linear regression, right? Like, so it has a couple of names. In statistics, this is called rich regression. Okay. And in neural network literature, whenever people do L2 regularization, they just call this weight decay. It's weight decay because you're decaying the weight to 0. Is that clear? Okay, so now that we have learned gradient descent, right? Like we can actually do gradient descent with L2 regularization. We don't need to do closed form solution. So I can take the loss function, which is 1 over 2n summation I is equal to 1 to capital N y of xi given w minus yi the whole square. This is my least square error plus lambda times summation over j wj square. So that is the L2 norm penalty, right? So now dou loss by dou w0 is going to be the first part we already know. It's summation over n I is equal to 1 to capital N y hat minus yi, right? Plus when you differentiate the second term, it becomes 2 times lambda times w0. Okay. Similarly, dou loss by dou w1 is going to be 1 over n summation I is equal to 1 to capital N y hat minus yi times xi plus 2 lambda times w1. Is that clear? So it's really easy to implement gradient descent even for L2 regularization. Like, so all you have to do is to add these terms, then everything is same. Okay. Okay. So now let's look at the geometrical intuition of like what L2 regularization is trying to do. Okay. So I can take my minimization problem, which is minimize y minus xw transpose y minus xw plus lambda times w transpose w, right? I want to minimize this function with respect to w, right? So this minimization problem, I can actually convert it into a constraint minimization problem, okay, where I would be minimizing y minus xw transpose y minus xw, okay, sorry, subject to the constraint that w transpose w is less than or equal to eta. I'll tell you what eta is. Okay, so typically eta is proportional to 1 over lambda. Okay, so this is an example of an unconstrained optimization problem. There is no constraint there, right? So I just have a function, I'm minimizing the function, right? But here, I'm writing the same optimization problem in a constrained manner, like which means I'm interested in minimizing this error function. Okay. When I'm minimizing, I put an extra constraint. The constraint is I want my weights to be within a range. Okay. So the L2 norm of the weight to be within a range. Let's say I want W transpose W to be less than or equal to eta. So when it's inversely proportional to lambda, which means when lambda is very high, the eta is going to be very small. If I set a very high lambda, it means I want a very small weight. So which means eta is going to be very small. Is that clear? Now, what kind of equation is this? Huh? Well, yes, but like what kind of function does it represent? Like, so if I have to expand this, it's basically saying W0 square plus W1 square is less than or equal to eta. Sorry? No, it's a circle. This is a circle, right? Like so this represents all the points inside the circle W0 square plus W1 square is equal to eta, right? So this means whenever I do L2 regularization, okay, what L2 regularization is doing is first it's deciding a circle surrounding 0. Okay, so it says, okay, I'm going to consider just solutions in this subject. Okay. I will not go outside the circle. This ensures that the weight doesn't grow. Right? Now, how big is the circle depends on your lambda. If your lambda is very high, the circle is too small. If the lambda is very low, the circle is too big. Say that what happens when the lambda is 0? Yeah, you cover the whole space, right? Like, so then there's no constraint. When lambda is 0, there's no constraint. Like, so it goes back to the vanilla regression, like linear regression. Okay. When you put a value for the lambda, that is when you're doing L2 regularization, and depending on the value of lambda, the circle is going to shrink. Is that clear? Now, here's the interesting thing. When you decide the circle or when you decide the lambda, you don't know where the solution is. Like, what if the solution is not within this circle? Right? So what if my solution, the true solution, is here? So this is the true solution I want to reach. But because I'm doing L2 regularization, L2 regularization is putting constraint that I can only deal within the circle. Now, what do you think would be the solution? Like geometrically, like what would be the solution that L2 regression, like or rich regression will arrive? Yeah, yeah. Yeah, so basically something that is closest to the point in the circle, right? So if you have your loss function which is centered around here, right? Which means you have a bowl which is centered around the dot. Like, so the contour map would look something like this, right? So whenever this contour intersect with the circle, that is the point you will stop, right? So this is your solution for ridge regression. Solution for ridge regression, while this is the actual solution. Is that clear? As you can see, you're not getting into the actual minimum, but it is okay. Why? Because that is the minimum for the training loss. We don't care about just minimizing training loss. Like, we care about not overfitting and having better generalization. Is that clear? Any question about L2 regularization? Okay, so now that we have seen how the idea of regularization works, which is basically to put some constraint, right? Now we can play around with the constraint. Like, we don't need to do just L2 regularization. Like, so, like, what if I do L1 regularization? Okay, so L1 regularization means my second error function is going to be just absolute value of W. That's the L1 norm. Okay, so which means I'm interested in minimizing Y minus XW transpose Y minus XW plus lambda times absolute value of W. Minimizing with respect to W. Right? When you try differentiating this and setting it to 0, you will find that there is actually no closed form solution for this error function. This is a perfect example where gradient descent is the only way in which you could solve this function. Is that clear? So let's do the gradient descent. But before that, maybe I'll tell you the name for this thing. Like, so when you do a linear regression with L1 regularization, it's called lasso regression. So discuss. Okay. So I'm going to compute the gradient. So the loss in this case is 1 over 2n summation I is equal to 1 to capital N y hat of xi given w minus yi whole square plus lambda times W. Right? So we know how to compute the gradient for the first one. Like, so what about the gradient for this term? So what is the gradient of absolute value of W? Yeah. So what is dou is by dou W? So this is not defined at W is equal to 0. Okay. However, it's 1 if W is greater than 0 and minus 1 when W is less than 0. Yes. So depending on the value of the W, you're going to get a gradient of plus 1 or minus 1. Is that clear? So this is doable, right? So now let's look at L1 regularization, but from the constrained optimization perspective. So the L1 regularization, the unconstrained version is basically minimize y minus xw transpose y minus xw plus lambda times q, right? So the constrained version of this is going to look something like this. Minimize y minus xw transpose y minus xw, okay, subject to the constraint that the L1 norm is less than or equal to eta. Okay, so this equation will look something like this. So W0 plus W1 is less than or equal to eta. Again, eta is proportional to 1 over lambda. So now what would this figure look like?
This equation and this circle equation, where did we get them from?
What do you mean by that? Well, I'm just saying that these are equivalent. They are equivalent. Like, so this is just an alternative way of this one. Oh, this is just the expansion of this, right? So I'm just expanding this here. There's no equal to eta. So what kind of figure is this? It's not circle. It's a square. Is it a square? It's a simplex. Okay, so it's almost like a square. Like, so it. Well, maybe I'll draw it and then you'll see it. So basically, this means that you want the absolute values to sum to eta, right? So which means you can go in both directions for both the values, and like, so the sum should be close to eta or equal to eta. So which would look something like this. Okay. Now instead of putting a circle, I'm putting a simplex and say, oh, like I want my weights to be not outside this. Like I can only move around this area. Okay. Now, again, let's say my solution is somewhere here. Okay. Now, what do you think would be the solution that the L1 regularization converges to? Yeah. Same idea as before, right? Like, so you can just draw the contour map and see where it intersects. Okay. Now this part is a little bit not obvious. Like, so, like when you have the simplex constraint, there's a very high chance for the contour to integrate, like to intersect in the axis. Okay, so your solution, well, this is 2D, but like in high dimension, like you will find that the solution almost always lies in one of the axes. So which means that your solution would have a bunch of zeros for weights. Okay, or in other words, L1 regularization helps you to get sparse solutions. Okay. By sparse, I mean like it is actually setting up some of the weights to be zero, exactly zero. Unlike L2, which just tries to reduce the weight as much as possible to zero, L1 sets some of the weights to zero outright. Okay. So in other words, it's actually doing some sort of implicit feature selection. Who is talking? Okay. So other words, it's implicitly doing some feature selection. Okay. So it is reducing, it's setting some of the features to zero, which means they are probably not important for the prediction that we care about. Is that clear? So if I have to implement the gradient descent update equation for this, it's going to look something like this. So W0 is going to be W0 minus alpha times 1 over n summation I is equal to 1 to capital N y hat minus yi plus lambda times 1 if W0 is greater than 0, or W0 minus alpha times 1 over n summation I is equal to 1 to capital N y hat minus yi plus, sorry, minus lambda times 1 if W0 is less than 0. Is that clear? Okay. So we have seen two ways to do regularization now, like L1 and L2. Okay. Yeah. Yeah. Well, it helps us to set some of the features to zero. So which means it helps us in removing like non-important features. Okay. Yes. Any other questions? Okay, so I think that concludes our discussion on linear regression completely. Now I want to go back to the nearest neighbor approach that we started with, right? And try to contrast between these two classes of solutions, okay? So if you, just as a quick recap, the nearest neighbor approach that we saw in the first week, right? Like, so it's basically the prediction y hat is given by 1 over k summation xi belongs to the neighborhood of x, yi, right? Where nk of x is basically the top k neighbors of x, right? So what is nearest neighbor doing? It's basically finding the top k nearest neighbors and computing the average of their prediction and considers that to be the prediction for the given x. Do you remember that from the first week? Okay. So what are the hyperparameters of this algorithm? What are the hyperparameters of this algorithm? Yeah. K, okay. The number of neighbors. So K is a hyperparameter, like, right? So then also the neighborhood definition. So like, how do you define neighborhood? Is it based on Euclidean distance, Manhattan distance? Like what kind of distance you're using? Like to compute the neighborhood, right? But in general, I think nearest neighbors makes this assumption that the function is locally smooth. So locally, if we take an average, that should be a good representation, right? This is a big assumption. Is that clear? Okay, so now let's try to compare and contrast linear regression and k nearest neighbor regression. Okay, so if you remember our discussion from the first lecture, Linear regression is a model-based approach, while k nearest neighbor is a model-free. Okay, so what do I mean by that? With k nearest neighbor, there is no model, right? Like, so we just store all the data, and whenever we want to make prediction, like we go search the database for nearest neighbors and compute the average of their predictions, right? On the other hand, the benefit of linear regression is like we are actually training a model. Like we are fitting a model, which is W0 plus W1x. So once I fit the model, do I still need to keep the training data? No, right? Let's say I have a million data points. Which is going to be faster, linear regression or k-nearest neighbor? Yeah, KNN, why? Is that true? Okay. Okay, so are there any other answers? Like, so which is going to be faster when I have a million data points? Or if I have to generalize this question further, which is going to be faster at scale? It could be million, 10 million, 100 million, okay? Which is going to be faster at scale, yeah?
Multiple neighbors.
Yes. So with linear regression, you're going to fit W0 and W1, right? Or whatever, like the weight vector, like it could be 10 weights or 20 weights, it doesn't matter, okay? So once you fit the weights, at prediction, you are just executing the equation, right? Which is actually very fast. However, with k nearest neighbor, with million data points, for every prediction, you're doing a nearest neighbor search with million data points. At scale, this is actually a very slow operation. Like, so, like, let's say you have 100 million data points or a billion data point, right? Like, so as the data increases, nearest neighbor search is costly. Okay, so at scale, linear regression or in general any model-based approach actually wins over nearest neighbor search simply because the scale doesn't matter after learning. Like, so you can just throw away all the data, just use the model. Is that clear? So in some sense, linear regression is actually learning the parameter from the data. And this learning is non-trivial. Okay, so this helps. However, with k nearest neighbor, there is no learning. Okay. Now, because of this, prediction is actually faster with linear regression, while prediction is slow again. Is that clear? However, there are other differences. Like, so for example, linear regression is a smooth line. It's just a line, right? So the solution by linear regression is smooth. Okay. But with k nearest neighbor, the solution is not smooth. Okay, so not a smooth line. Okay. Is k nearest neighbor a linear model or a nonlinear model? Is it linear or like what kind of lines you would fit with k nearest neighbor? I'm doing KNN regression. Okay, so what kind of line I would fit with k nearest neighbor? So let's actually do an example. So let's say I have x, y, and just as an example. Okay, if I do linear regression, then we know that this is the solution, right? It's a line. If I do k nearest neighbor, what do you think the function would look like? Yeah. Sorry? Like a stairs. Okay. So the way in which okay, let's say I do two nearest neighbor. Okay. So what does that mean? At any point, you're going to find the two nearest neighbors and take an average. Right? So from here to here, or maybe not up to that, maybe from here to here, approximately, the two nearest neighbors are these two things, right? The average, so basically the line is going to look something like this. Then the average is going to be the average of these two guys. Then the average is going to be the average of these two guys at until some point, and then the average of these two guys. So it's going to look something like this, right? So because we are taking average of the nearest neighbors, locally it's going to look like a straight line. The moment the neighbors change, there's a jump. So is this a linear model or a nonlinear model? Okay, this is an obvious question. Does it look like a line? No, it's not a linear model. Okay, so k nearest neighbor is not a linear model. It's a nonlinear model. Okay, so this is linear, well, as the name suggests, right? Like this is nonlinear. Okay, now because linear regression is linear, like it's just fitting a line, right? Like it's actually more stable. K nearest neighbor, on the other hand, is less stable. It jumps around, like with a very small change in the x, like you will find a different answer. Okay, so the core assumption that linear regression makes is that the solution is linear. That is a very strong assumption. Linear regression makes this assumption that, oh, my answer is going to be linear, so I'm fitting a linear line. Like I'm just fitting a line, right? The core assumption that k nearest neighbor is making is that things are locally smooth. Is that clear? So in terms of the terminology that we're going to develop in next week's class, okay, so this actually means that linear regression has very high bias, okay, and low variance. However, k nearest neighbor has very low bias and high variance. Okay, so what do I mean by high bias and low variance? We'll talk about it next week. Is that clear? Any questions so far? Yeah. Okay. Well, so the actual explanation comes next week, but like just to give you some intuition, right? Like so why I say k nearest neighbor is low bias while linear regression is high bias. Linear regression is high bias because it makes this very strong assumption that everything is aligned, right? Which means the solution is not going to change too much, which is what I mean by low variance. Okay, it has a very high bias that things are just aligned, which is also good because then it has very less variance. Things don't change, it's just a line. On the other hand, with k nearest neighbor, it is not making this line assumption. Like it's actually non-linear, right? Like so it can actually model really complex functions. Okay, so which is why I say it has low bias. Okay, it doesn't make strong assumptions, but because it doesn't make strong assumptions, it's going to have variance in the solutions because like every small change is going to make things look different, like because it's nonlinear. Is that clear? but we'll see a more technical definition of bias and variance of algorithms in the next week. Okay, so we are finishing a bit early today, which is good. And so far, I introduce you to a very basic machine learning problem, which is regression, right? Like, and we looked at two classes of algorithms. Like, so one is k-nearest neighbor, the other one is like a model-based linear regression algorithm, right? Like, so this is a good time to do more theoretical foundation. So next class is going to be more theoretical in the sense like we will really think about what is a good solution for a problem. Like what does these different classes of solutions even mean, right? Like, so which one is more preferable over this, right? So we're going to look at more basic foundations. So we will stop here. And as usual, this is my office hours. Like, so if you have any questions.